Hi, I'm Shania.
I'm Emily.
I'm Nina.
And I'm Kanha.
This is the UASB design final presentation. So wastewater is water that is used by humans. This used water tends to contain urine and fecal matter, pollutants, chemicals, and pathogens. These compounds come from a variety of sources such as household waste, schools, industries, and farming. Because water is a universal solvent, it's very difficult to separate water from these harmful pollutants. As a result, wastewater must be treated before it's put back into the environment safely, and in the US, this is generally done so through sedimentation, biological degradation, and chlorination. So the importance of wastewater treatment. If wastewater is left untreated and put back into the environment, it can pose serious health and environmental problems. When wastewater reaches a clean drinking water source, this can pose a serious health risk to a community. Pathogens in the wastewater can destroy crop production and cause waterborne diseases such as cholera, diarrhea, and hepatitis A. Wastewater also contains organic decaying matter and nutrients such as phosphorus and nitrogen, which can cause eutrophication, which is the term for excess nutrients. This can cause algae blooms, which causes oxygen deprived conditions, which makes it harder to sustain aquaculture. In the past, Agua Clara has focused mainly on providing sustainable and inexpensive drinking water. However, it's changing its focus more on wastewater. So UASB Design Team's purpose is to create a gravity-powered UASB reactor that will be tested in Ithaca's wastewater treatment plant this summer. This will be a big step for Agua Clara's venture into wastewater treatment. In a UASB reactor, wastewater is pumped to the bottom of the reactor through Influent pipes. The wastewater flows through a sludge blanket, which is composed of millions of methane-producing bacteria, and biogas is collected at the top, which can be used for energy, and cleaner wastewater can exit through the effluent pipes, which can be put back into the environment safely.
Okay, so this is a general schematic of what our UASB reactor will look like. So here we first have the influent system, which is a tipping bucket influent system. So the water is going to come down through the tipping bucket influent system to the pipes, and then water is going to flow from the pipes into the reactor where the sludge blanket is, and then it's going to come out of the effluent pipe. And then here we have a sludge weir that's going to get rid of any excess sludge that's produced from consuming organics in the wastewater. And then here's our biogas collection tank, which is where the methane and the carbon dioxide will go. So a couple of goals that we have for this UASB reactor is to make sure that it's gravity powered, so no electricity is needed, and ideally we'll be producing electricity from burning off the biogas that we collect. And then we also want this to be able to make this smaller for rural communities, so that it can efficiently remove COD from wastewater. And then we also want to make it easy to fabricate and a modular plant, so we can easily take it apart and put it back together in case we need to maintain or clean or upgrade any sort of parts. So this semester UASB Design has really focused on refining previous teams' designs. We really wanted to be able to create a design that we can fabricate in the Ithaca wastewater treatment facility by the end of this semester. And so we really focused on dimensions and what parameters we need to figure out dimensions. And so recently we've made a shift to smaller reactors so that we can fit more reactors in the space that we have at the Ithaca wastewater treatment facility. So here we have a CAD model of what it's going to look like. It's switching from our original reactor is 3 feet in diameter, now we're 10 inches in diameter. And then it's generally the same system, so influent tipping bucket system into one pipe instead of 4, and then an effluent and a sludge weir. And then we've also added an FOG removal system that gets rid of any fats, oils, and greases. So the reason why we shifted to smaller reactors is so that we could test multiple, because we don't have that much space. And then we also have a clear pipe that's our main reactor, so we can see anything that's going on, anything we have to, any issues we have to address. So our design for the Influent system is a tipping bucket. This creates pulsated flow, and basically what it'll do is it'll increase upflow velocity despite having low flow rates, which will sort of lift the sludge blanket often and make sure that no sludge settles, which will eliminate preferential pathways and make sure that the sludge blanket is active. It'll also declog any sort of, ideally declog any clogging that might happen in the pipes.
Okay, so from the tipping bucket system, the wastewater will enter a drain pipe, which is indicated by that green arrow there. And so the purpose of the drain pipe is to first slow down the influent wastewater so that gas bubbles inside of the wastewater can escape. The drain pipe is also important because it determines the head gain per dump of the tipping bucket. And that's because the bottom of the drain pipe is in line with the water level inside that clear canister of the UASB reactor. And so the head gain per dump is just the cross-sectional area of the drain pipe divided by the volume of one dump of the tipping bucket. Lastly, the drain pipe is important because in the future, when we scale up the UASB design and might have, 4 influent pipes, it will be useful to promote even flow throughout those influent pipes.
So another component that we've added into our UASB reactor is FOG removal. What we realized is that our initial large reactor, we were not taking into account fats, oils, and gases, and grease, which is what FOG stands for. So what we've added is this funnel FOG removal pipe. The bottom of the funnel will rest at the resting height of the water level within the reactor, so that after every tip of a bucket, when the water level rises, it will remove all of the fat, oil, and grease which are lying at the top of the water, as it is less dense than the wastewater and water we are treating. This was not taken into account in our previous reactor, and we realized it's something we should and have to take into account in our new design. At the bottom of the funnel, there's going to be a deflecting panel, which ensures that none of the methane gas bubbles created within the reactor enter this funnel and cause it from not being able to remove any of the fats, oils, and grease.
Okay, so the next question is, how does the treated water get out of the UASB reactor? And the answer is our effluent system. So as you can see here, it's kind of a T shape, and the arrow there points to that T. And that's kind of an important part of the effluent because it determines what the water level inside of the UASB reactor will be. And the hydraulics of that are more in depth described in the appendix 2 if you're interested. Next, okay, so yeah, you see the water level there. And then these arrows show how water from inside of the reactor will actually exit through the effluent. So there are holes in the top of the pipe that goes into the reactor, and that location is important because it prevents gas bubbles that are rising in the reactor from entering, and so then we won't get methane in the effluent. Another important feature of the effluent design is that it has that pipe stub there, which serves to maintain atmospheric pressure in the reactor, which prevents the effluent line from becoming pressurized and sucking methane from inside of the UASB reactor down into the effluent. And so then here's just some pictures of flanges which will be used to create end caps on the clear PVC pipe which we are using as our canister. And so these are a great option because they firstly provide stability, and they can be made airtight with gaskets. They'll also be flat, so we can rest the tipping bucket system on top of the flange. And then this arrow here just points to a bolt, and we will use those to further stabilize and level the UASB reactor. So just an important part of what we've been doing this semester is developing a Python model of the UASB, and we've used that to determine what are the best dimensions to use. So basically our main constraint is the upflow velocity within the UASB reactor. We want that to be fast so that it fluidizes sludge granules. And so what we've done is determined a relationship between the diameter of the UASB, the geometry of the drain pipe, the minor losses in the system, the height of the drain pipe, or the head gain per dump the tipping bucket, the diameter of the influent pipe, and by doing that, we've been able to figure out reasonable dimensions for our reactor.
So now that we've figured out what we want to do and the reactor we want to create, we've laid out some future tasks for future semesters to take over and try to execute. So the first task is to finish the on-shape model. At the end of the semester, after meeting with Monroe, Ruth, and Ed from the wastewater treatment plant, we decided we wanted to go with the smaller reactor, and we need to complete the on-shape CAD drawing for this design. What we want to do different for this model compared to our initial large 36-inch diameter reactor is we want to make sure that this design is parameterized. What this means is we want to be able to input variables such as angles of pipes, heights of pipes, and the code or the drawing automatically adjusts itself to account for these. We also want to finalize the heights and positions of the influent pipes, effluent pipes, FOG, and sludge weirs. These are all going to be dependent on one another, and we want to ensure that the heights we're setting, all of these, ensure that there's no problems with taking out sludge granules or not effectively treating the wastewater. Additionally, this design is appearing to be a lot more stable than our initial design, but if necessary, we want to figure out if a support system will be required, and if so, how to implement it. The next step would be fabricating the first reactor. The first step of this is completing a parts list, as we want to estimate the cost of one of this reactor. Costs are going to be a big part of Agua Clara moving forward in wastewater treatment, and it'll also help us understand how much it will take to build one of these reactors. After finding out the parts list, we want to purchase each part and create the first reactor to be implemented in the wastewater treatment plant. The objective of this is to make sure we know that the tipping bucket is working. We can finalize the height of the influent, effluent, FOG, and sludge weirs, and this will all be done by creating a whole UASB reactor, ideally by the summer of 2019, so that we can test and see how our reactor is doing at the treatment plant. Finally, we want to modify our Python code. We want to modify it so that it takes into account set values such as upflow velocity or diameter size. These are factors we already know and want within our reactor, and currently our code does not take into account for that. For example, our current code requires us to input the influent pipe, and it will give us it will output the upflow velocity within the reactor. As we know what we want the upflow velocity to be, we want to modify our code so that it will give us the pipe size given the upflow velocity that is desired. This is intended so that the reactor can be modified and upscaled in future years. This semester, this team has been working on this quote: water treatment is saving humans from the environment, wastewater treatment is saving the environment from humans. We're going to take this idea and continue it in future semesters. If you have any questions, feel free to contact us at any one of these emails, and thank you.